record. So as people are walking in or entering, I'm going to share my screen and give you a couple of reminders. So you have due tonight, you have a bunch of homework. You've got a written assignment due at midnight and a couple of Newton assignments due at midnight. So hopefully you've been working on the Newton assignments. So the written homework is everyone has their own graphing problem, and the online homework is optimization. Let me share that. Hang on a sec. So if you go to Canvas, we're in week 12. So the homework due tonight, there's a written assignment, number 5, that's due at midnight. And if you haven't looked at it yet, you're basically supposed to follow 6 steps. And I want you to number your steps because I want other people to be able to understand which step, you know, what you're doing. On a test, I don't expect you to number your steps, but follow the steps. And then each person in the class has been given a unique function to graph. So you just have one graph to do. And it's kind of a long, you know, it might take a full page, possibly 2 pages, depending on how complicated your graph, your function is. So everybody has their own function, follow the 6 steps, write it out, number the steps, and this is all going to be posted. So this is a discussion board. So let's see, has anyone posted? Yeah, looks like a whole bunch of people have posted. So it looks like most people did not follow my instructions on embedding. So it looks like this is going to be kind of awkward for other people. So for those of you who have not done it yet, I don't want you to attach your picture the way these people have. It looks like Nicholas embedded his picture. So the way that you do it, let me show you for those of you who haven't done it yet. And if you want to do yours over again, that would be great, because unfortunately, when you attach a file the way that these students did, it looks like Richard had to attach 3 files. That means we have to download and open up 3 different files. It's a little bit of work for those of us who want to look at what you did. And I want other people to look at what you did. So what I want you to do is the following. If you click on reply, you can click on the embed image. Don't attach an image, embed the image. So when you click on embed image, watch what happens. It's kind of like, where's my image? You click on Canvas, and then you have a folder called My Files. So I click on My Files, and I don't have my homework picture in there yet. So my homework is, I've taken a scan, it's on my phone or it's on my computer. So what I want to do is I want to click on upload file. So if I click on upload file, then I can go to see if I have, so let's say, I don't know, I have a file somewhere. Let's say I want to upload this picture. There's a picture. That's on my computer. I select it, and now I can just click on update, and there is my picture. So that's how I want you to do it. So then when I click on post reply, everyone can see my homework, and they don't have to download a bunch of files. So that's how I'd like you to do it. Please, if you have the time to go back and repost your homework solutions, those of you who have already done it, I want you to do that. And those of you who have not done it yet, this is how I want you to do it. So, oh, so I'm gonna have to delete mine at some point. Once I figure out how to do that. Okay, so that's what I want you to do by tonight at midnight. Embed your photo, a JPEG. Let's see, did anybody do? Yeah, somebody did a PDF. So that you can't embed a PDF. If you can, Matthew, convert that to a JPEG or a PNG or JPG, and then you can embed it as a photo. So you can only embed photos. You can't embed PDFs. All right, so that is due at midnight. And then you have a couple of Newton assignments. There's two optimization assignments on Newton that are due at midnight. There's going to be more homework due Thursday. I haven't posted that yet. And that homework will be based on today's material. So you can do that after the exam. So the exam on Wednesday, here's what we're going to do. The exam on Wednesday, I'm not going to make you do Proctorio. I'm not going to make you log into Zoom. What you're going to do is you're going to download the test. I'm going to make it available at exactly 8:30 on Wednesday morning, and you're going to have an hour and 20 minutes to write your exam, take a scan, and then upload it to Canvas. And it will be an assignment on Canvas. Now I want to warn you, it has to be a PDF. You will be restricted. If you try to upload a JPEG, it won't, Canvas won't let you do it. So you must, so you have to upload a PDF, a single PDF, okay? A single PDF file. And that's because that's, as you know, I grade in GradeScope, and I can only upload PDFs. And if you upload something other than a PDF, that means I have to go and try to convert your file for you. So I'd rather you each convert your own files so that I don't have to convert everybody's file. And in fact, you won't be able to upload anything that isn't a PDF. So please make sure you know how to scan and convert to a PDF. Let's see. So another thing, I will post instructions. Let me show you a Canvas assignment. Let's see. Let's go to, I'm going to show. Well, I have to find one. Hang on a sec. I'm going to show you something you may not realize that you can do. That's not it. Hang on. Let me find all right, I don't have one easily handy, but I will post some instructions. So if you use like Google Drive or Dropbox, and you scan, say you've downloaded your test, you've printed it out, and you write your test, and then you take a scan with your picture. If you save your PDF file to Dropbox or Google Drive or you know, one of those, Google Drive, Dropbox, there might be a couple others I'm not thinking of right now, then you can upload them in Canvas from your computer or from any other device. So I'll post a little, a couple of screen images or a video or something to show you how to do that. If you haven't figured out how to do that, it's pretty easy. So you don't have to send yourself your PDF in an email. All right, let's see. All right, so the exam will be Wednesday. You'll have 8:30 to 9:50. Oh no, 8:30. You'll have an hour and a half. Okay, yeah, it'll be over at an hour at 10 a.m. You have to get it done by and uploaded by 10 a.m., not 9:50. So you'll have an hour and 30 minutes. So it's 10 minutes longer than usual just to allow for all the uploading. If you don't have a printer, of course, you can write the questions. Now, if you do have to write the questions because you can't print, you don't have a printer, then I ask that you write your questions or write your solutions. You don't have to write the exact question, but do it the same way I've done it on the test. So if I have problems 2 and 3 on page 2, I want you to only have problems 2 and 3 on page 2. And your first page has to be your academic integrity pledge. So if you don't have a pledge, I'm not going to grade your test, okay? So you have to have an academic integrity pledge. This is an exam you have to do by yourself with no help from anyone else and no, you know, unauthorized resources. No, you're not supposed to be using a book. You're not supposed to be using the internet. So you're just taking the test as if you were taking the test in the classroom, okay? But you have to have an academic integrity pledge. That's the first page of your test. And then the rest of the test is exactly as I've written it. So if the test is 7 pages long, the first page is an academic integrity pledge, and the other 6 pages are your solutions. That's what you're uploading. You're uploading 7 pages. The first page has to be your pledge. And I'll remind you of this. So that's going to be Wednesday morning. And the material on that test is just everything we've covered up through last Wednesday. So today's material will not be on Wednesday's test. Today's material will be on the homework you do for Thursday night. And I think that's it. And there's no quiz this week because we have an exam on Wednesday. And then next week's quiz will just be on the homework that you're doing for this Thursday. So the material we're doing today is on next week's quiz. All right, any questions about what I've just told you? Any questions about what's going on this week, the test?
Will there be like a PDF for the
test?
test? Yeah.
Yeah. So I'm going to upload a PDF and you can download that and print it. If you have a printer, that would be perfect. That's exactly what I'd love everyone to do. And then you scan it and upload it by 10 a.m. If you don't have a printer, then you can just open it up on your computer and then write your solutions. You don't have to write the questions, just write your solutions and number them. And make sure that your solutions, the problems that you do are just like the test. So what I said was the first page has to be the academic integrity pledge with your signature and your name. The second page, if there's only one problem on the second page of my test, then your second page just has one problem. The third page might have 2 problems. That's all you're going to put on your third page. And the reason is when I upload these to GradeScope, they all have to have the same problems on the same page. Otherwise, it's kind of a nightmare for me to navigate everyone's test and try to grade, because I grade 1 problem at a time. So I go through and I grade everyone's problem number 1, Then I go back and I grade everyone's problem number 2. And so GradeScope has to know where to find it. If problem number 2 is on page 3, that's what GradeScope is going to show me. But if you have problem number 6 on page 3, then I have to go do a lot of extra work to find problem number 2. So if you don't have a printer, it's really important that your solutions are all on the correct page of your whatever you're going to upload. You don't have to write the problems down. That's too time consuming. Just number it and then write your full, it's problem number 2, and then write your solution. You don't have to write down the problem because I know what the problem is. Any other questions about the test on Wednesday?
Does the printer have to be in your room like the last?
No.
Okay.
Yeah, no, because there's no video. I'm not video. Nobody's recording you. I am going to trust everyone. Okay, so you guys are on your honor, and that's why the academic pledge is so important to me. I want you to be honest, and I trust you to be honest. I have no reason to suspect anyone in this class, and I, you know, there might be, you know, cheating happens at DVC. When I catch it, I turn people in. I don't want to have to look for cheating on this test. I want to believe that everyone is being honest and doing their own work, not talking to other people, not using the book or your notes. So just take the test on your own with, you know, the way you would in a classroom. And yes, your printer can be in another room because it doesn't matter. Nobody's watching you. And I trust you, okay? Any other questions about the test on Wednesday? You can just unmute yourself and, okay. If you do have questions, I believe I have a discussion board topic called questions about exam 3. So post your questions there. The reason I want you to post them there is because I want everyone to benefit from the answer. If you ask a question and I answer it, I want everyone to have that information. And also, if you post a question about a specific problem that you're working on, somebody else might answer it. Another student might be able to help you. So that's another thing. There's on my old exams, I have not posted the solutions yet. I'm writing a reminder to myself. So there are old exams on Canvas, and where have I put them? I'll put them in this week's module because I think I have them linked in another module. So I'll make sure I repost the old exams. You can find them, and then I'm going to post the solutions to the problems that are relevant to our exam 3. I'll post the solutions by tomorrow night at the latest, by Tuesday night. So watch for that. So solutions to old exams will be posted by tomorrow night. Okay, I think that might be it for reminders. Can anybody think of anything else that's going on this week that we need to know about? I think that's it. All right, I will post reminders and discussion and instructions about the test also before tomorrow night, just to kind of, so you have an idea of what you're doing. You're basically going to do a Canvas, like a homework assignment, but you're only going to have an hour and a half to do it. Oh, and then after the test, sorry, at 10:10 a.m. on Wednesday, I want you to log into Zoom. Log into Zoom, and we'll have class. We'll just have, you know, an hour, or sorry, we'll have 50 minutes of class, but we'll have a new topic. And then that topic, you'll have homework due the following Monday night. Okay, so we're gonna have class after the test, after everyone submits their test, then you're gonna log in and join us for class. And I'll be here at 10:10 a.m. All right, if there are no questions, I'm gonna get started. So what we're gonna do today, as I said, is it's not on the exam, but it is, you will have homework due on Thursday night. There's going to be 2 little Newton assignments. I don't think they're going to be very long or very difficult. So I want you to just not think about them until Wednesday, and then you can do your homework after you take the test. So what we're going to do is we're going to learn about antiderivatives. I'm going to start with an example. So this is a word problem. So suppose we have a particle and it's moving along a horizontal line. And we know that its initial position is given by s of 0 equals 5. So s is the position function. And at time 0, the location of the particle is at 5, whatever units or centimeters or whatever units we're using. So there's a position function, s of t, and we know s of 0 is 5. And suppose it has velocity as a function of time. The velocity is v of t equals 3t squared plus 2t. So we're given a velocity function as a function of time, and we're given an initial position. And remember, velocity is the rate of change of position. So velocity is the first derivative of position function. So the question is, let's find its position as a function of time. So let's look for s of t. All we know is v of t and s of 0. Since we know that the velocity is the first derivative of the position, so we know v of t is s prime of t, we call s of t the antiderivative of v. So if v is the derivative of s, then s is the antiderivative of v. So if we let f of t be t to the third plus t squared, that looks like it could be an antiderivative. In fact, it is. It's one antiderivative. Because if we differentiate f, we get 3t squared plus 2t. So that could be the position function. Because when we differentiate it, we get the velocity. But the problem is, if we plug in 0 into f, we just get 0. We don't get 5. So it is an antiderivative, but it's not the one we're looking for. But any antiderivative of v of t has to have the form g of t equals t to the third plus t squared plus k for some constant. Because if we differentiate that, we'll just get 3t squared plus 2t, because the derivative of k is 0. So k could be any constant, and t to the third plus t squared plus k will still be an antiderivative. So we have a lot of choices. We have infinitely many real numbers available to us to use for k. So if we need g of 0 to be 5, that means that 5 would be 0 to the third plus 0 squared plus that constant k. But that just means that k has to be 5. So we started with some function g of t. We don't know what it is, but we know it has to have form t to the third plus t squared plus a constant k. And we said, well, if g of 0 is 5, then that means that constant has to be 5. So that tells us that the position function, the one we were looking for, should be t to the third plus t squared plus 5. Hopefully. So all we have to do is check and make sure it works. So let's, oops, not b prime of t, sorry. So v of t is the derivative of s, and so if we differentiate this, we get 3t squared plus 2t, and that works. And also, if we plug in 0 into the position function, we do get 5, so that works. So that's the function we were looking for. S of t has to be t to the third plus t squared plus 5. All right. Any questions about that? So we just started with an example just to show what an antiderivative means. It means we're given a function and we're told this is the derivative of something, and our job was to find the antiderivative, the function that if we differentiate it, we'll get the derivative that we were given. But we saw that there are many choices. If you're given something that's a derivative and you're looking for an antiderivative, we had infinitely many choices in this example because there was a constant that could be any constant and it would still work. But that's why we were given the initial position, S of 0 equals 5. That allowed us to find a specific constant for this specific situation. So the problem that we just solved is basically, this is called an initial value problem. And this is a classic problem in an area of mathematics called differential equations. You're given the derivative function and an initial value of the function you're looking for, and you're able to find the function. When you guys take, and many of you will take Math192, which is called differential equations. It's a 5-unit math class. You take it after you've taken 3 semesters of calculus. If you're an engineering major, you will take that class. And you'll do lots of initial value problems. In fact, you will also do some in Calc 2. Calc 2 does a little bit of differential equations. So we just solved an initial value problem. All right. So I'm giving you a couple definitions now. So, and notice I'm using capital F. So capital F is sort of notation we often use for antiderivatives. So capital F is an antiderivative of little f if capital F prime is equal to little f. So it's really important that you don't write capital F when you mean little f. So be very careful with your notation. We're using capital letters to denote antiderivatives of the lowercase, the corresponding lowercase letter. And capital F of x plus c, where c is any, it could be any constant. It represents an arbitrary real number. So capital F of x plus c is called the general antiderivative. We also call them indefinite integrals. So it's called the general antiderivative or the indefinite integral. And we'll learn more about what the word integral means later. So it's the general antiderivative of the function little f. Or we call it the indefinite integral of the function little f. I should say little f of x. So here's a quick example. Oops. So let me move things around here. Oops. Sorry, okay. So in my example, capital F of x is equal to negative x to the third minus cosine of x plus c. That is the general antiderivative, or the indefinite integral, of the function little f of x, which is negative 3x squared plus sine x. So I did this kind of quickly, but if you differentiate the first one, capital F of X, you'll get little f of X, right? So that means that capital F of X is the antiderivative, the general antiderivative. And that's because it's a general antiderivative because it has an arbitrary constant C. And that's also called the indefinite integral of little f of X. So basically we're going backwards now. We're starting with derivatives and we're anti-differentiating them to find the antiderivatives. So I'm going to remind you of a corollary to the mean value theorem. One of the corollaries. We had two corollaries to the mean value theorem. So corollary 2 said if f prime of X and g prime of X are the same for all numbers in some interval, then the two functions differ by a constant on that interval. So f minus g, that's a new function. And it's a constant function, means it's equal to just a constant. It's a horizontal line, basically. That also means, so if f of X minus g of X is equal to some constant, then that means that f of X is equal to g of X plus that constant. So you have two functions that have the same derivative. So one of them is just a constant plus the other one. They differ by a constant. All right. Okay, I can see people still writing. All right, I'm going to change slides. So here's another example. So suppose that f of X is equal to x squared plus 2, and g of X is equal to x squared minus 1. So when we differentiate those two functions, we see f prime of X is 2x and g prime of X is 2x. They have the same derivative. So by that corollary, f of X has to be equal to g of X plus some constant k, because they both have derivative 2x. So the first one is just the second one plus some number. And we can tell by looking at them that if we just take g of X and add 3, so g of X is x squared minus 1, right? So if we add 3, we'll get x squared plus 2. So x squared plus 2 is equal to x squared minus 1 plus 3. And so that means that f of x is just g of x plus 3. So let me write that. And so now I'm going to show the graphs. So these are just parabolas. They're both opening upward, right? X squared has just a positive 1 in front of it. So the coefficient is positive, means it's opening upward. And they just have different y-intercepts. So f of x looks like this. It's a parabola opening upward, y-intercept at positive 2. G of x has the exact same shape, but it's down, it's lower. So the y-intercept is negative 1. And if we look at any point x, right, and look at the corresponding points on the curves, the tangent lines are parallel. So I just drew a tangent line on the graph of f at the point x, and I drew the tangent line on the graph g at the same point x, and they're parallel. And that's because the derivatives are equal. F prime of x is the same as g prime of x. So those two tangent lines have the same slope. And also we can tell, because they have the graph of f and the graph of g, they have the same shape. We can see that the space between the y-coordinates, right, that gap between f of x and g of x, the y-coordinates at the point x, that gap is f of x minus g of x, right? The y-coordinate on f minus the y-coordinate on g, and that's positive 3, the gap. And it's the same, the gap is the same all along the curves. The gap should just be 3 everywhere. Oops, so sorry. Okay. All right, more examples. So let's find the general antiderivative, or otherwise known as the indefinite integral, of each of the following. So write down these 3 functions. The first one is little f of x equals x squared minus 2x plus 2. The second one is little g of x is 3 times e to the negative x. And the third one is little h of x, which is 2 cosine 3x. So we're going to find the general antiderivative of each one of these. Okay, so what I want you guys to do is try these on your own. We'll talk about them, but go ahead and try for each one of these to find the function, or it will have an arbitrary constant. Each one of these is going to have an arbitrary constant. So find a function such that when you differentiate that function, you get the given function. So for little f of x equals x squared minus 2x plus 2, I want you to find another polynomial, capital F of x, whose derivative will be little f of x. So I want you to anti-differentiate each one of these. Give it a try. And each one of them, each one of your answers should have a plus c or plus k, because we want the general antiderivative. So when you come up with a function, test it, see if it worked. So always check your answer by differentiating your answer and make sure you get what you're supposed to get when you differentiate. So write down a polynomial in the first one and then differentiate it to see if you get the given little f of x. So for example, if I try this, if I go, okay, it looks like my antiderivative is just going to be x to the third minus 2x squared plus 2x plus k. And then if I differentiate that, I get 3x squared minus 4x plus 2. And that didn't work. That is not going to work. I just have to check my answer, right? So this one didn't work, so I'll have to try again. So make sure you always check your answer. That's the nice thing about antiderivatives. You can always check your answer just by differentiating. Sometimes guessing the antiderivative is difficult, and you might have to do it a couple times. But the nice thing is you can check each one of your answers. And when you check, it gives you a little information about how to tweak your next guess. So let's talk about the first one really quick. So I just gave an example of a guess that didn't work. So my guess was capital F of x equals x to the third minus 2x squared plus 2x plus k. But when I differentiated it, I got 3x squared minus 4x plus 2. So the 3x squared didn't work, right? I'm supposed to get just x squared. Well, it looks like that 3 was the only problem. So maybe my guess should have had a 1/3. If I had tried 1/3 times x to the third, then I would have gotten, when I differentiated, I would have gotten 3/3 times x squared. And also in the second term, 2x squared didn't work because then when I differentiated, I got 4x and I needed a 2x. So perhaps I should have just left it as x squared, because then when I differentiate, I would just get 2x. So my guess was wrong, but it wasn't that wrong. So my final answer should have looked like this. Capital F of x equals 1/3 x squared minus, 1/3 x to the third minus x squared plus 2x plus c. And I check and I go, okay, that's because that's my answer, because differentiating it gives me 1/3 times 3x squared minus 2x plus 2 plus 0. And when I simplify, I do get x squared minus 2x plus 2. So always check your answer. In fact, you're justifying your answer. You're saying, this is my answer, and I know it's correct because when I differentiate it, this is what I get. So that's using the definition of general antiderivative. Big F of x is the general antiderivative, means that the derivative of big F is equal to little f. And I should, let me say that here, it's equal to little f of x. So let's look at the second one. The second one is g of x equals 3 times e to the negative x. So we know the exponential, natural exponential function, e to the x, the derivative of that is just e to the x. But the derivative of e to the negative x, using the chain rule, gives us negative e to the negative x when we differentiate it. So this one, when we go backwards, when we anti-differentiate, we have to take into account that the chain rule does result in giving us the opposite. If the function we're differentiating is negative, then the derivative will be positive. If the function we're starting with is positive, then the derivative of that is negative. So if the derivative is already positive, like this one, this is the derivative. We're looking at little g of x is the derivative of something, and it's positive. We know that the original function had to be negative. So capital G of x has to be -3 e to the negative x plus c. And that's because when we differentiate it, g prime, capital G prime of x is going to be -3 times e to the negative x times -1, using the chain rule, plus 0. And that's +3 e to the negative x, which is little g of x. So we had to take into account that minus sign, that negative x in the exponent, using the chain rule. That affects our derivative. And then the third one has a cosine. It also has, it's a composite cosine of 3 times x. So the chain rule comes into play in the third one as well. So we're looking for the antiderivative of 2 times cosine of 3 times x. So you might have to, it might be trial and error. You might try a couple different things. But the answer should be h of x is 2/3 times sine 3x plus c. And I check by differentiating. So if I differentiate this, h prime of x is going to be 2/3 times cosine 3x times the derivative of the inside, which is 3, plus 0. So the chain rule means it's the derivative of the outside, which is cosine of 3x. So the derivative of sine is cosine, and it's positive. But then I have to multiply by the derivative of the inside. The inside was 3x, and the derivative of that is 3. And so this is, 2 times cosine 3x, and that is little h of x. So finding the antiderivative of a function sometimes takes a couple of guesses, but always check each guess, and you'll get the hang of it after practicing with a bunch of functions. You'll start to recognize things. But it's just like when you're in an algebra class and you're learning how to factor. It's trial and error, but each time you try, you multiply it back together to see if you got the right thing, and if you didn't, you can tell what went wrong, and you can fix it on your next guess. So it's the same idea. First guess, then check, then guess again. Any questions on these examples we just did? Okay. All right. So let's, so what we just did was we found general antiderivatives. So now if you want to find a specific antiderivative, you have to have some additional information to get rid of that constant. And that's why we use initial values. So to find a specific antiderivative using an initial value, so that would be called an initial value problem. We're going to do an example. So let's do another initial value problem. Suppose f of x is 4 minus 3 times 1 plus x squared to the negative 1. Let's find the antiderivative of this. The antiderivative, we're going to call it capital F, such that capital F of 1 is 0. So this is our initial value. So what I want you guys to try this one. Try to find the antiderivative, the general antiderivative of the little f of x function, and then try to solve for that constant using the initial value. So step 1 is to first find the general antiderivative. So I want you to try that. So just come up with the general antiderivative. So everyone should try step 1. So the first term is 4, and we know that 4x is probably the antiderivative of 4, because when we differentiate 4x, we just get 4. But the second term is a little more complicated because it clearly is going to use sort of an anti-power rule and an anti-chain rule, right? So let's try f of x equals sorry. Let's try capital F of x equals 4x minus 3 times the arctan. So if you rewrite 1 plus x squared to the negative 1, you get 1 over 1 plus x squared. And that you should recognize as the derivative of the arctan. And then we have to add a constant. So capital F of x is 4x minus 3 arctan x plus k. And that's because if you differentiate, you will get the original f, little f of x. So now in the second step, we have to find that constant k. So to find the constant k, we use that initial value, capital F of 1 equals 0. So we're going to take this new function and we're going to plug in 0. So that means 4 times, sorry, we're going to plug in 1, excuse me, and set it equal to 0. So 4 times 1 minus 3 arctan of 1 plus k is 0. So now we have to evaluate this. So 4 times 1 is 4. And then the arctan of 1 is pi over 4. So we get 4 minus 3 times pi over 4 plus k is equal to 0. And if we solve that for k, we just get k is 3 pi over 4 minus 4. So putting it together, the function we were looking for is just 4x minus 3 arctan x plus that constant, 3 pi over 4 minus 4. So that's called an initial value problem. We're given a derivative and an initial value of the function we're looking for. We first find the general antiderivative and then use that and the initial value to solve for that unknown constant and then put it all together. All right. Okay. So let's try. So there's, as I said, there's 2 handouts, and the first handout on Canvas is just these 2 examples. I just to save you time writing them out. So this is on the first handout, the lecture examples. It says, suppose a particle moves along a straight line with initial position 0 centimeters and initial velocity 1 centimeter per second. We're given two initial values, the initial position and the initial velocity. And then it says if its acceleration at time t is given by this function a of t equals 3 cosine t minus 2 sine t centimeters per second squared, it asks us to find the position of the particle at time t. So notice we're given acceleration this time and asked to find position. We're given the acceleration function and we need to find the position function. So in the first initial value problem at the very beginning of class, we were given only a velocity function and asked to find position function. And we were only given one initial value, the position at time 0. And also in the last example we were given the first derivative and one initial value of the function we were looking for. Here, we're not given the first derivative. We're actually given the second derivative. The acceleration, remember, is the second derivative of the position. The velocity is the first derivative, the acceleration is the second derivative. So that's precisely why we had to be given two initial values. We've got the second derivative here. So we're two levels away from what we're looking for. We're looking for the position, but we're given the acceleration. So we're two levels. The first derivative is velocity, the second derivative is what we're given. So we need to go up. We need to anti-differentiate twice. And that's why we need two initial values to get rid of two arbitrary constants. So let's try it. So the acceleration is the derivative of the velocity. So a of t is equal to v prime. So v, the velocity function, should be the antiderivative of the acceleration. So let's try 3 sine t plus cosine t plus c. So let's see if that works. If we differentiate that, we should get 3 cosine t plus 2 times negative sine t. So that is negative 2 sine t plus 0. So we did find the general antiderivative of the acceleration, but we have an arbitrary constant in it. So the initial velocity was given to us as 1 centimeter per second. So when it says initial velocity, that means t equals 0. So we can plug in v of 0 is equal to, well, it's given to us to be 1. So we can plug in 0 into our velocity function. So 3 sine of 0 plus 2 cosine of 0 plus c is equal to 1, because we're given that v of 0 is 1. So if we evaluate that, so sine 0 is 0, so we get 2, and sorry, cosine of 0 is 1, so we get 2 plus c equals 1, because cosine of 0 is 1 and sine of 0 is 0. So now if we subtract 2, we get c equals negative 1. So that means we found the velocity. The velocity function is 3 sine t plus 2 cosine t minus 1. So that is just the velocity. We still haven't found the position function. Since the velocity is the first derivative of the position, we can find a general antiderivative for the position function. So let's anti-differentiate that v of t that we found. So the antiderivative of the sine t is negative cosine t. So the position function will be 3 times negative cosine t. And then the antiderivative of the cosine is going to be positive sine. So we're going to have 2 plus 2 times sine t. And then the antiderivative of -1 is negative t. And then we have plus a constant. So S of t is 3 times negative cosine t plus 2 times sine t minus t plus some constant d.
Professor, we can't hear you. We can't hear you.
Professor. Professor Gomez.
Sorry. I'm gonna unmute you, Robert. Are you trying to say something, Robert?
Oh, I was putting paper saying that your mic was not working for a while.
Thank you. How long was that going on?
Like a couple minutes.
No, sorry, I just noticed it. I was using earbuds that apparently weren't working, and then I tried to switch to my speakers. I'm really sorry about that. Did somebody send me a chat? Because, oh, yeah, it looks like somebody sent me a chat. Sorry, I didn't have my chat window open. That's my fault. Sorry about that. You can't hear me. Oh, mic not working, can't hear you. It looks like that's been going on for about at least 2 minutes. Sorry. Let me go back and explain my steps. So we were given the acceleration, right? So we were given the second derivative, s double prime of t. So our first step was to find the, first we found the general antiderivative of that. That's the general antiderivative of the acceleration. And then we used the initial value of the first derivative, because that was initial velocity is equal to 1. So v of 0 equals 1. We used that to get the actual velocity function. Then step 2 was to anti-differentiate the velocity to get the position function that we were looking for. So we got, first we got the general antiderivative of the velocity. So notice there's a constant d, and we used the initial position s of 0 equals 0 centimeters to solve for d. And then that's how we got our final answer. So the point I was trying to make, and you probably didn't hear me say it, sorry. The point I was trying to make is in this problem, it was an initial value problem, but we were given a second derivative. So we had to go back up 2 levels. We had to anti-differentiate twice. And each time we anti-differentiated, we got an arbitrary constant. So we needed an initial value to find that constant. And we had to do that twice. Well, that's why we had to be given 2 initial values, not one. Not just one initial value would have worked. So in initial value problems, when you take Calc 2, you might do this, but definitely when you take Math 294, you might be given, you know, the 5th derivative, and you'll need 5 initial values to get all the way back up to the function you're looking for. So that's why we had to do it twice. Are there any questions about this example? I'm really sorry about my audio issues. I seem to be having them a lot lately. All right, let's look at that second, I believe, the second example on that handout, that first handout. So we're given 1, 2, 3, 4 graphs. The red one is the graph of little f. Little f of x is the red graph. The other 3 are candidates for the antiderivative of f. So I want you guys to try to figure out which of those 3, A, B, or C, is the antiderivative of f, just using the graphs. So your job is to decide which of the 3 graphs, A, B, or C, is the antiderivative of the function f. So f is the derivative of one of those 3 functions, and you have to figure out which one.
Can you guys hear me right now? Yes, okay. I'm gonna try these. A couple weeks ago, I used these and somebody said they were staticky. Am I sounding staticky? No? Okay. All right, let's try these. All right, has anybody come up with an answer? Which one of the graphs A, B, or C is the antiderivative of F?
Yeah, I think I got an answer.
You got an answer, Jeff? What did you decide?
I think I got B.
B. Can you explain why?
Yeah, sure. So the antiderivative is like it's kind of like the area under the curve, and so it's a line that represents that. And so for F, there's a really big negative space between the x-axis and the graph of F at the beginning. And where F intersects the x-axis, you can kind of see with the graph of B that the value is getting more and more positive, because now F is also in the positive region, and the area under the curve of F is growing larger in the positive direction, as is B, which is why I chose B.
Okay. So that's beyond what we've learned in this course so far. So we don't know anything about area under a curve, or what negative area means. In fact, area can't be negative, so that doesn't really, but I know what you mean, because it sounds like you're using a previous calculus course to do that. So did anyone else do this without talking about something we haven't learned yet? Did anyone else do it? Thank you, Jeff. I understood your explanation, but I don't think a typical Calc 1 student at this point in the course would understand that. So does anyone else have an explanation that doesn't use area under a curve? Anyone else? No one? So next week, we'll talk about area under a curve. I think next week, yeah, after the exam, we will talk about that, but we haven't learned that yet. But what Jeff was referring to was that point. He was talking about that point where the graph of F crosses the x-axis. So let's say capital F of x is the antiderivative we're looking for, right? So capital F of x, when we differentiate it, capital F prime has to be little f. So when you look at the place where little f crosses the x-axis, so let's call that point D. So F prime, not F prime, well, little f is capital F prime, right? So little f of D is 0. So if we look at the two graphs that have horizontal tangents there, looks like those are candidates. Graph A is not a candidate because it doesn't have a horizontal tangent at point D. So at point D, the derivative, little f, is 0. So the graph of the function we're looking for has to have a horizontal tangent at that point D. Well, there's two of them. The green one, which is C, and the blue one, which is B. B is the one that Jeff decided was the answer, and I think he's right. So why is C not the answer? Well, so we can see that the tangent lines, the slopes of the tangent lines are changing at that point D. So, so both of them have 0 derivative there, but little f, the red graph, little f changes, as Jeff noted, Jeff said this, little f crosses the x-axis and it goes from negative to positive there, right? So the function we're looking for has to, its tangent lines have to go from negative slope to positive slope, right? So B prime changes from negative to positive. So the blue graph, notice that the tangent lines are negative before the point D, and then they're positive. The tangents are positive, have positive slope after the point D. So if you differentiate B prime, the derivatives are negative and then positive. But if you look at the other one, the other graph, C, the tangents, the slopes of the tangents change from positive to negative. So that one doesn't work. So it looks like, yeah, Jeff was right. The answer is B, right? Yeah, B. So B is the antiderivative of the graph of F, the red graph. So without talking about area under a curve, we can do this using just slopes of tangent lines. So the F, the red graph, is basically a graph of slopes of tangent lines. And so we had to find the graph whose slopes, tangent lines, changed from positive to negative. Or sorry, from negative to positive. Negative to positive. And that was B. So Jeff was correct, but he was using something we haven't learned yet. And so I think most of the class probably couldn't follow that. Any questions about that one? All right, where are we? 10:02. It's time for our break. So we will take 10 minutes and then we have another worksheet and that's also posted on Canvas. The second worksheet, when we come back, we'll get into some groups. I'll put you guys into breakout rooms. I have to look at the worksheet. I might skip a couple problems. I don't know, I have to look at it again. But when we come back, I'll tell you which problems I want you to do and I'll put you guys into groups. So it's 10:02. Let's come back at 12 minutes after. Okay? I'll see you guys in 10 minutes. All right. Oops. All right, you guys, let's see who's back. I don't see anyone. All right, I hope you guys are back. I see no faces. So I'm going to start putting you into group. There's Robert. Thank you, Robert, for, for showing up. Let me get you guys into some groups. So we are going to work on, let's do all of problems 1 and 2 in our groups, and I'll see how far people get. And then I'll bring you guys back together once I think everyone's done with problem 2. So do them in order, do all of problem 1 and problem 2. Let's see how far we get, how long that takes us. So I'm gonna get you guys into some groups. Let's see. We've only got 13 people, so, 13. So we lost a couple of people. So let's see. Okay, so I'm going to put you guys into groups. There's going to be groups of 3, 1 group of 4. I want you to do them in order. Do number 1 and then number 2. And do them in order. Don't skip around, because I want to make sure everyone in your group is doing pretty much the same problem at the same time. Please compare answers and help each other figure out if you've made a mistake. So I want everyone to do problem 1 and problem 2, and I'm going to come around to each group and see when almost every group is finished with number 2. I'm going to bring you guys back together to talk about them before we move on to number 3. All right, so head to your rooms.
So, Professor? Hello, I can't hear you. I think you're muted, but I did get kicked out of my breakout group.
I am muted. Sorry about that.
No,
Who is that? Caesar? Okay.
yes,
All right.
I was with Jeff.
All right. Thank you. Sorry about that. I had my headphones off. I was muted.
No, you're totally fine. I'm sorry.
That's all
For
right.
some reason, it kicked me out.
I'm glad you're back. Okay. I'm putting you back in the right room. Yeah, Jeff is all by himself. Okay. Here you go. Hi, I'm bringing everyone back together so we can go through problems 1 and 2 and then answer questions on any problems, other problems that people got to. I just want to make sure everyone is good on the first 2 problems before we leave today. 5, 4, 3, 2, 1. Okay, everyone is back. So I wanted to go over all of problem 1 and problem 2 before we leave. We've got 13 minutes. And also then see if people who got beyond problem number 2 have any questions. If some people did get further, they might have questions, but let's make sure everyone is on the same page with problems 1 and 2. So I'm going to go through problem 1, kind of the first couple of problems kind of quickly. So in part A, you should get the antiderivative here should be capital F of x is equal to 2x squared plus 7x plus c. And if you differentiate that, you can check my answer, but that should be your final answer. And then in part B, you should get the antiderivative is capital G of theta, which should be sine of theta plus c. And if you differentiate that, you can make sure I got the right answer. And I think I did. Now, I'm going to switch slides because I think pretty much everybody got through A and B pretty easily. So part C, we have to sort of take into account the chain rule here. So capital H of t should be our antiderivative, and it should be 1/2 e to the 2t plus c. And just to check, to make sure that's right, differentiate it, and you get 1/2 e to the 2t times 2 plus 0, and that simplifies to e to the 2t. So I got the right answer. Now F, this one is really important, and there may be some people that did it but didn't get the right answer. So make sure you understand what I'm doing here. So the answer here should be capital F of R is equal to the natural log of not just R, but the absolute value of R. And I'm going to show you why this works. Because the absolute value of R is equal to, it's a piecewise function, right? So it's equal to the opposite of R if R is a negative number, and it's equal to R if R is a positive number. And we're not allowing R to be 0 because it's 1 over R. R can't be 0. So now that means that the derivative, so d dr of the absolute value of R is equal to, oops, sorry. I meant to say the derivative of the natural log of the absolute value of R. Okay, so I'm going to differentiate the absolute, I'm going to differentiate the natural log of the absolute value. So it's a chain rule. So the derivative of the outside is, I'm going to do, so sorry, let me back up here. So this is going to be a piecewise derivative. So it's the derivative of the natural log of the opposite of R, if R is negative. And it's the derivative of the natural log of R, if R is positive. So let me kind of make some room here. So now I'm going to differentiate this piecewise derivative. So the derivative of the natural log of negative R is 1 over negative R times the derivative of negative R, which is negative 1. So that's if R is negative. And then the other one, the derivative of the natural log of R is just 1 over R if R is positive. So notice that in both cases, so in the first part, 1 over negative R times negative 1 means it's 1 over R. So in both cases, we get 1 over R. So that means the derivative, sorry, my handwriting is bad. The derivative, that's a d dr of the natural log of the absolute value of R is always going to be 1 over R. So my answer, I should have had a plus C. My answer for the antiderivative was correct. The antiderivative of 1 over R is the natural log of the absolute value of R plus an arbitrary constant. So I did it kind of quickly, but the proof of what I did is over here. The proof of why I'm correct. It's the antiderivative is not just the natural log of R. It's the natural log of the absolute value of R. And so R can be any real number except 0, and we can anti-differentiate 1 over R. Anybody have a question about what I just did? I've lost a bunch of people. So if you have a question, just unmute yourself. So this is a formula, an anti-differentiation formula we can use for 1 over R. All right, now, oh, somebody's chatting with me. Hang on. It's clear. All right, thank you, Luis. Sorry. Oops. Sorry, I just annotated something accidentally. All right, let me go back to the worksheet. Sorry, there's something. I want to get rid of this annotation business. There we go. All right, back to the worksheet. So that brings us to part E. So in part E, I wanted you to come up with another formula. So in part E,
it's f of x is x to the n, where n is any real number except -1. So if n is -1, then x to the -1 is just 1 over x. And we already did that in part D. So we don't need to get a formula for that. But if n is any other real number except -1, we want to come up with a formula. And I'm calling the formula the anti-power rule. And I just want to remind you, the power rule for differentiation was this. The power rule said if you have f of x equals x to the n, then the power rule said that the derivative is x times, n times x to the -1. So that's for differentiation. So we want to come up with a formula for anti-differentiation, and that's why I'm calling it the anti-power rule. So here, the formula that you should have come up with is this. You raise the exponent by 1, but then you have to divide by whatever that number was that you got. So it's x to the n plus 1 divided by n plus 1. And then we have to add a constant. So this is a formula that you will use for the rest of the semester. And you'll have to memorize it. So you'll do lots of problems so that you can memorize it. And then using that formula, we can do part F. So part F is f of x equals the cubed root of x squared plus x times the square root of x. So the hint was to first rewrite everything using exponents and then use the formula that we got in part E. So I'm going to rewrite this function, f of x. So the cube root of x squared is really x to the 2/3. And then x times square root of x is x times x to the 1/2. So that's x to the 3/2. So now, using the formula that we got in the previous problem, we can anti-differentiate this, and we get x to the 2/3 plus 1 over 2/3 plus 1 plus x to the 3/2 plus 1 over 3/2 plus 1. And then we can, plus c, don't forget your constant. And then we need to simplify this. So this turns out to be x to the 5/2 over 5/2, but I can write that as 2/5 times 2/5 instead of divided by 5/2, it's times 2/5. And then this one is x to the, sorry, that was 5/3. My bad. That was 5/3. And that was 3/5. Sorry, the first one is 3/5 times x to the 5/3. The second one is 5/2. And it's 2/5. So I just used the formula from part E to do this, and then I simplified. So 2/3 plus 1 is 5/3, and the reciprocal of 5/3 is 3/5. 3/2 plus 1 is 5/2, and the reciprocal of that is 2/5. All right, then the last one in problem 1. Oops, did I? Oh. Sorry, I don't have it written down. Let me see if I can find it. Is this it? Yeah. So part G is a G of theta is 2 sine theta minus secant squared theta. So you should get for the antiderivative should be, so the antiderivative of sine is negative cosine. So this should be -2 cosine theta. And then the antiderivative of secant squared is just tan theta. And so problem 2. So I'm just going to write down the answer to problem 2 since I ran out of time, but I want to make sure people can check their answers. So problem 2, your final answer should be the antiderivative is x to the 5th minus 1/3 x to the 6th plus 4. So this is just the answer. I didn't have time to go through that problem. Are there any questions on any of this worksheet? Either problems 1 and 2 or some other problem that you did? Just unmute yourself if you have a question. I don't see any hands up. All right, you guys, I'm going to post some reminders about the test on Wednesday. It's at 8:30. We're not going to log into Zoom for the test. You're just going to go to Canvas and you'll find it. You will download, print out the test, scan it, upload it as a single PDF. If you have to write down the problems, I need you to write the academic integrity pledge on the first page, and then the rest of the test should be in just like the way I've written it. And you will be timed. It will be an hour and a half. And then we'll have class after a 10-minute break. We'll meet on Zoom after the test. All right, you guys, homework for tonight and an exam on Wednesday. And I have student hours right after class. I'm just going to take a little break, and then I'm going to come back at 11:15 if you want to talk to me today. Otherwise, I have student hours tomorrow from 11 to 12:30, same place. All right, I'll see you guys in a couple of days if I don't see you sooner. We're going to try to end this meeting. Here we go.